Assalamualaikum and hi everyone. This is pre-recorded video 15 for chemical bonding. In the previous video, we have concluded subtopic VSEPR that can be used to predict the molecular geometry. In this video, we are going to learn about another theory in chemical bonding, which is hybrid orbital theory or HOT. This is a video HOT part 1. Generally, hybrid orbital theory is a continuation from valence bond theory. We expect that the number of bonds formed by an atom depending on the number of unpaired electrons. For example, chlorine generally forms one bond and has one unpaired electrons. Oxygen with two unpaired electrons usually forms two bonds. However, carbon with only two unpaired electrons generally forms four bonds. For example, methane, CH4, which is well-known compound. In principle, the bonding in carbon can be explained like this. Four unpaired electrons are formed as an electron from the 2s orbital, which can be promoted or excited to the vacant 2p orbital. So we do know that carbon has orbital diagram of this. Okay, so this is 1s, this is 2s, and this is 2p. So carbon electron configuration is 1s2, 2s2, and 2p2, right? So 1s2, 2s2, and 2p2. All right, so this is an electron configuration for carbon, which is more than enough energy is supplied for this promotion. Okay, so for hybrid orbital theory in its promotion from the formation of two additional covalent bonds. We can refer to this orbital diagram, the first case. Okay, the first case is ground state electron configurations. You have to mention this is ground state, which is a normal state. Okay, carbon should only have two bonds, which is this in 2p, right? 1, 2. Okay, so the second case here, if a 2s electron, okay, 2s electron originally has two electrons, but if it is promoted to an empty 2p orbital, then four unpaired electrons can give rise to four bonds, making 1, 2, 3, 4. Because this electron can be promoted here. Okay, so the case these four orbitals become mixed or hybridized to form bonds. Okay, so this is ground state, this is excited state, this is hybrid state. So you have to mention this ground state, excited state, and hybrid state in if you're answering this kind of question. So towards the end, a new hybrid orbital is produced, which is a hybrid of s and p orbital, producing sp3. This is how you draw the orbital. At first, all single orbitals are drawn like this, as px, py, and pz. Okay, these four orbitals are combined to generate four sp3 orbitals. Okay, so these are all four sp3 orbitals, and then we combine together actually to become a set like this. Okay, to see it more clearer, let's look at the sp3 orbital for carbon atom here. The blue loops before the overlapping of CH bond head-on with singly occupied H1s hydrogen 1s orbital. On the right side, you can see the orbital overlapping blue and red loops from different atoms of carbon and hydrogens. We should remember that there is a relationship between type of hybrid orbitals and its geometric arrangements and vice versa. If we know one of them, we can predict the other one. This is it. Type of hybrid orbital sp, its geometric arrangements is linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, sp3d2 octahedral. Depends on the how many orbitals are there. So sp got 2. For example, beryllium in beryllium difluorides, or octahedral 1 from sp3 and d2, 3 plus 2 plus 1 is 6, right? So number orbital is 6. So for example, sulfur in sulfur hexafluoride. That's the end of for hybrid orbital theory part 1. Thank you. See you in the next video.